Okay, here we go. So share screen. Have this, we have. Okay, so the clock. The idea today is first we will do a presentation on this atmospheric model work. Yes, of course, we can devote 2 weeks to learn how to use properly WRF. So it's a complex model, very friendly, but complex. So if you haven't started, it's recommended that you spend a good year learning how to use it. But it's worth it because it's a very powerful research tool. This is WRF is in a sense an atmospheric model. In the way CROCO is an ocean model, is a professional tool, well developed, and used mostly for regional simulations. Even you can use it for the complete atmosphere. I mean, you can but it's mostly to use to represent the circulation in an area where you have boundaries from a larger model. So we will see a brief description, and we'll check how it's organized, and at the end I will present the basic reference that this model uses. Well, that's a logo. First, most important, this is how you pronounce WRF for you Trekkies out there. And basically, WRF is an atmospheric model used for research and forecasting. Forecasting is very important in atmospheric sciences, so it's a big focus on that. But it can be used for research, and as CROCO, it can be used for idealized simulations, so simplified cases. As the code is non-hydrostatic, is compressible and conservative. So you need sound waves in the atmosphere. You cannot suppress them as in the ocean model. And even now we're relaxing that constriction in CROCO. In the same way that CROCO has 2 time steps, the baroclinic and barotropic, CROCO WRF has also 2 time steps for fast processes and slow processes. In this case, the fast processes are the sound waves, for example. So we need to calculate those with a smaller time step, and then we mix the data. So it's the same approach that you can see in CROCO, aiming at computer efficiency. The model has the complete equations, a very complete set of equations for the hydrodynamics. So you can work on the order of meters or synoptic scale. For our applications, in the way one uses an atmospheric model with the ocean models, when you reach 1 kilometer, that's considered like a high resolution. So that's that 1 kilometer, even you can go lower than that. 1 kilometer, I think, is quite a lot. Even your grid cells can be 1 kilometer. Actually, the correct representation of the energy in these kind of models is on the order of 6 dx, 6 delta x to 8 delta x. So it's if you have 1 kilometer cells, it doesn't mean that you can resolve all the flows on correctly with the proper energy at that scale. So that's something to keep in mind. It's well advanced in the sense that has, well, it's Arakawa C-grid as in CROCO, and they have advanced advection schemes, for example, in advection, fifth order, where you can get a very numerical results. And deep convection can be explicitly profounded. Parallelization is pretty good in WRF. And you have several add-ons in the same way we have this biology and these floats modules. With WRF, you can do chemistry, atmospheric chemistry for pollution studies, fire, the WRF fire for fire propagation. There's a data simulation module, very well developed. And even if it's just one code, you actually have two codes called WRF ARW. That's the one we use. That is a continuation of the MM5 model. And the WRF NMM, that is more a large scale, is more related to the old ETA model. So typically when we use WRF, we use the WRF ARW code. Okay, so this is what I was mentioned about the spatial scales, how the energy in the y-axis is related to the wavelength we're resolving. So you can see that in this figure, the energy associated with the forecast follows what is expected from that red line up to around 7 delta x. And this is something we didn't discuss in detail in CROCO, but it's something that also happens for ocean models, where your effective resolution is on the order of 7 to 10 delta x. So your grid size is not exactly the most resolved scale of your simulation. There are several parametrizations that we have to implement, or we have to choose when we do an atmospheric simulation, since there's no definitive equation there's no equation of conservation for a process, or there's no fixed way or a standard way to do this, represent these processes. So when you do a simulation with WRF, you must understand that you have to choose one model for the planet boundary layer, for the surface layer, your microphysics, your land surface model, how you treat long wave radiation, short wave radiation, and cumulus parametrization. So for all these processes, we will see that there are many choices to do. So in any good paper that uses WRF, you will see a table that says, okay, for these processes, for this, I use these physical schemes in my study. In this case, for example, you see here that they use the MRF planet boundary layer, for example, or the Lin et al. Microphysics approach. So this is a flow diagram of how you do simulations with WRF, with WRF, yes, the ARW model. You need external data sources that typically this is very complete. Typically, you just follow this path. Sorry. So you have terrestrial data. That is what we equivalent to what we use to create the grid file in CROCO. You have data from your external model, and you use what is called the WPS WRF processing system to create the input files. And then you can use the next step is to use a code called real.x to to create all the netcdf input files for WRF. So this is the standard route to create input files. If you have data, if you do data simulation, you can use all this section of the flow diagram. That is very rare. You need a lot of data to start and a very good computer. And this box mentions all the idealized simulations you can do with WRF. So basically, you input the data, you do use WPS, then real, and then you have your WRF simulation. And post-processing can be done with a lot of tools. NCL, Python tools now are being expanded for this, but it's a netcdf file, so you can use whatever you want to, whatever you like to use for netcdf processing. Most of these are you have to program the routines, but in there are some graphic interfaces for this. This is what I want to mention about the time split scheme for WRF, where the inner step, the fast step, is the acoustic loop. As mentioned, you have a C grid on the horizontal and on the vertical, in the same way we discussed with CROCO. So you have really 3 grids, what you call stagger grids, for the U, B, and scalar variables. And as in CROCO, you have a sigma vertical coordinate that follows the terrain. CROCO is implementing a hybrid coordinate now, but by default you use a sigma coordinate. But in WRF you tend to add more levels near the surface, since this is the area where we are mostly interested in simulations. One difference with CROCO is that the upper layer, in this case, for the atmospheric model, is held as a constant. So you don't have a free surface there. You have what is called a rigid lid in a constant pressure, in this case, in the upper level that you define in your model. And that's the width of your atmosphere at the end. The advanced schemes I was mentioning in WRF, this is an example of that. In the left column, we have a 5th order upwind advection scheme that's more advanced, and the second, and in the right column, we have a 2nd order advection scheme. And you can see that if we increase the grid size as we go down in the files, the representation of these processes is worse with the 2nd order advection scheme. So in this case, we can have an equivalent accuracy with a 200-meter grid if we use the 5th order upwind advection scheme. And with the less precise scheme, we need to increase the resolution down to 50-meter grid. So we need will be 16 times, or MATRIX will be 16 times larger in that case, because we have a 4-fold in each direction. We have increased it, split or grid 4 times in each of the axes. So that way we have correct processes without the need of increasing the resolution. So that was a bit about the physics of the model. As a regional model, we need to provide boundary conditions and initial conditions from some source. For forecasting, one of the resources that is available is the GFS, global forecasting system. Is from NOAA. It's quite a quite a useful resource since it's very easy to access and free. It has started in 1991. These are the standard forecasts we receive, and it's now based in a finite volume cube sphere. The forecasting system has improved the methodologies using to do forecasts. You can get grids at half a degree or a quarter of a degree globally. And you have hourly outputs for the first 120 hours and every 2 hours up to day 16. So you can do forecasting. You can have forecasts up to 16 days, but in practice, I think if you go beyond 7 days, is not very, you can get anything beyond 7 days, but up to 16, 5-7 days is something you can trust. In the vertical resolution, this product has 46 levels. And the output is in GRIB, that is a standard format for atmospheric sciences, and also NetCDF. And you have some links there about these data sets. So if you're doing forecasting and you will use WRF, most of that you will use this as your boundary condition for that. So there's another very useful source of information that is FNL, that is based on this forecast. So what they do is they take the initial condition for each of the forecasts that is done. The forecasts are done every 6 hours every day. So they take this initial condition file and they improve it, adding more data to improve the representation of the atmospheric field for that particular time step. And the FNL is not a model by itself, but it's a collection of these improved boundary conditions every 6 hours. It's a one grid product with 26 vertical levels, or I think it has increased to 32. But you get in GRIB 2 format. That is one of the input formats for WRF, for the pre-processing stage of WRF. Those products are from the United States, from the European Center of Medium Weather Forecasting. You have one of the products that is is being used a lot now, that is proven very accurate and very useful, is called ERA 5. You have now results from 1950 to the present. And the resolution of this product is about 1/3 of a degree every hour. It has a very high vertical resolution, 137 levels in NetCDF formats. And it's a very good resource for if you want to do historical runs. It has replaced what was called ERA interim. And well, so basically you have ERA interim was the previous model from the European Center, and there are some papers. This is from Stopa and Chong about comparing the winds in the ocean of these two models. If you want to make sure your winds will be right for your model, you need to check the input for your atmospheric model. So there are a few papers comparing this. In particular, in this paper, they found that the ERA interim's winds were more consistent in time, but they had the higher velocities were underrepresented. So you have the higher, the very high winds, they were not well represented in this product. In comparison, the CFSR product from NOAA was better at representing high winds, but it has a changing bias in time. This is because what I understand is when they improve the model, they just keep going with the new model. And they don't take the time to redo the runs with all the improvements. So they just keep improving, and the model is improved from that time on, but you don't reprocess previous years. So just to mention the idea that as any model, you need to be aware of what is your input and what's the quality of your input before using this input. This is a global view, but it can be different for your particular area of interest. So we mentioned about these physical parametrizations. This is a list from the COMET program is a very useful program from NOAA that is presents a lot of study material on atmospheric sciences. So these are all processes that are important for atmospheric representation. And these are all processes that we have to somehow represent in our model. And they're very complex. And some of them you can use formulas. Some of them you can use a statistical approach. And this can be done because either the spatial scale is very small, so we will have to decrease the grid a lot to represent them. So that's very expensive computationally. Or the exact formula is also very expensive, or we don't know the formula for that. Yeah. And it's complex because at the end, all of them are related. Convective processes, cumulus are related, microphysics of clouds with turbulence, radiation, land surface model, the boundary layer. And the typical thing that we do with WRF is we just choose them separately, but they are related to each other. For example, the parametrization of solar radiation represents a flux of energy in the surface of the Earth. And the Earth surface parametrization represents a segment of the latent heat on the ground. So that provides a boundary condition for the upper layer, and that affects the turbulence, that affects the heat and humidity, that affects the clouds, and affects the radiation. So we go full circle trying to understand how one thing affects the other. Yeah. So that's a better diagram for this. So when we choose, these are a list of some of the parameterization we have to choose with WRF. And if we choose one, we are affecting another one. So we cannot just say, okay, I will pick the best for microphysics, the best for radiation independently. It's the best combination of them. And for example, in precipitation, in this study of 1997, they found that the total volume of water from rain is highly sensitive to what kind of parametrization of cumulus you choose. So when you go and use WRF, you have to use, you have 11 options for that cumulus parametrization. That starts from no parametrization, the Kane-Fritsch scheme, the Betz-Miller-Janik scheme, etc. It's very, very complex, and we have to choose one of these. I think the best recommendation I can give you if you want to do a simulation with WRF is just check the papers from your area and check what's the most common, what are the most common schemes used for your area, and start from there. If it works, great. If not, start looking at changing one or another. But it's a complex process. Now, the key files for Word, there are mainly, I would say, two key files in Word. One of them is called the namelist WPS. Namelist, like the namelist from we saw yesterday for Pisces. And this is the files you use to configure your domain. So here you define how many domains you use. Well, nesting is also available in this atmospheric model, very much in the way that we use a grid. You can think of them in the same way. It's very easy to nest in Word, and you can add new, in the same way you can use parallel nest or telescopic nest. So in this case, for example, when in the field start date and end date, we have two columns because this file is meant for two domains. And we choose when to start and when to end each of these domains. And like in this file agreed fixedgrids.in, we have to say which is the parent grid and where's the starting point of the nested grid, in this case 31 and 17, for example. We can see also what's the nesting ratio, in this case 3, as the same as in CROCO, or 5 as in CROCO. It's very similar in that sense. Just keep in mind that when you want to configure your domain, you have to think about this file. The name is WPS. This is the domain creation, the domain design, and that's for the WPS is for the Word processing system. The other key file is the nameless input file. It's a file that combines what is in CROCO, the CROCO in, the cppdefs.h, and the param.h file. That's an input file that has a bit of the, well, maybe not the param.h. That's more in the previous one. It's more the CROCO in and cppdefs. You have the physics. You can choose the physics. You can choose the time step. You can choose how often you save. One difference with CROCO is in Word you cannot choose easily. You can, but it's not straightforward which variables you're going to save, for example. But one difference with CROCO is that in Word you can change the physics with this input file. The way the code is designed, you just compile once and that's it. You don't worry about the changing like in CROCO, when you change the types, you don't worry about that in Word. If you change the domain, you don't worry about that in Word. Normally, like in these supercomputer environments, the Word executable is compiled once and that's it. It's very, very friendly in that way. And you change, when you change the physics or you change the domain, you just change them in the input file, when you create the input files, or you change it on the nameless input. So the basic reference for Word, I will say, are these: the Scamrock and Clamp is the classic reference to make a reference about using Word. You have the NCEP1 reanalysis, that is the grandmother of reanalysis. There's this reference for CFSR, ERA interim, ERA 5, and well, this comparison I mentioned of Stopa and Chung about comparing winds and wave on ERA interim and NCEP 5. So let me show you a bit something else. Okay. So,
Doctor,
see?
I have a question, please.
Yes.
When you use a couplet model like WRF and CROCO, the spin-up decrease in both models or is maintained similar?
The spin-up?
Ajá. O sea, si tengo entendido que el modelo WRF, como es un modelo atmosférico, el tiempo de estabilización es más corto, ¿no?
Sí,
Pero, oye, en el
yes,
caso de, por la memoria del océano y de la atmósfera, pero
yes.
cuando acoplas el modelo uno con otro, ¿cambiaría eso o no necesariamente?
No, the spin-up time uh, for you, your restriction is with CROCO. CROCO has the longer spin-up time, I would say, and it depends more on the initial condition and the boundary condition than the forcing, atmospheric forcing.
Ah,
So
ok.
I think you will be constricted by the initial condition anyways.
Ah, ok. Otra pregunta, disculpa.
Yes, yes.
Um, ¿Cuáles serían los errores clásicos, ¿no? O estos blow-up que se presentan al hacer el acoplamiento entre uno y otro? Hay errores
Uh,
típicos, por ejemplo, en la parte del croco, ¿no? Que cuando cambias la grilla lo vuelves más fino, te olvidaste de cambiar la parte temporal que tienes que también disminuirla. En el caso de este tipo de acoplado, ¿cuáles serían los más clásicos, ¿no? Que casi siempre cometemos ese pequeño error.
I think probably the time step, but we can discuss that in during the afternoon with the we will have time to ask Sven about these classical errors in coupling. But I think I will I will guess it's more there are many files to adjust and you have to worry that all of them are correct. So it's more on the organization than in the physics, I think.
Ok, thank
So
you.
let's see. Let me show you quickly a brief demonstration of or talking about WRF. This is a virtual machine we built for teaching WRF also here at University of Concepcion. It's also available if you're interested. And WRF has several packages that are very friendly. One of them is the WRF domain wizard that help us to design a domain for a simulation. This is like the CROCO tools for now. So we just give a name to your domain, and then we choose what area we're going to represent. With a map, we choose the projection. So check at this point. I say, okay, I want to do a representation of this area. Or let's go to the Benguela case. Something like that. Then I do update map. And by default, this model says, okay, you want this area. Let's start by splitting it in 100 by 100, meaning we don't want a too small grid for a domain, but a too coarse grid. We need at least 100 elements in each direction to have a good resolution. And that means that the distance between each grid cell is about 28.5 kilometers. We can change this to a close number, okay? And this will give us this. And now we're presented with this file that is an editor for the nameless input, this key file I mentioned. So if we see the text editor, we can see all the details that you can define in this. all the aspects about when the simulation, all the time aspects, when it starts, when it ends, the time step of the output. The calculation time step is here, and it's given more or less by there's a proxy rule for 6 times dx. Here we have the size of our domain, 100 by 100, but 28 vertical levels. We haven't done a nesting. And here in this nameless input file, we have this physics. It's one domain, so we have to choose all these numbers for which physics parameterization we will use for each case. This is, in this case, it is for cumulus parametrization. So this is the key part on the physical side, on the equations. On the equations you will use in your atmospheric simulation, and you can change them on the run. You don't have to recompile for this. More or less, I think this is the most important part. So you go back and you say, okay, this is nice, but I want to do a nested case because I did a nested case in CROCO. You can do this. You can do this and say, okay, I will do this nested domain, but it's more I like it better here. And you will have one domain and my subdomain. Change that, and now notice that we have, well, 3 columns, but we will use just 2 columns, max domains equals 2. And each column is related to one of the domains. So the first domain is 100 by 100, and the second domain is 94 by 106, and is the nesting rate is by 3. So one domain is, the first one was 30 kilometers, and the second one then is 10 kilometers, where the dx and dy. And in the same case, you can choose a different physics for each domain, although this is not recommended. Normally, you just keep the same physics for each one of them, except for cumulus physics, where below 5 kilometers, you have to set 0, for example. So with this, we're configuring the most important file in WRF, that is the nameless input. But with the previous steps, we were, with this graphical user interface, creating the nameless WPS. And well, these are the steps to create the input files. It's a bit slow, so I will not do them now. Okay, so what do I get here? If I go to the domains directory, if I go to the CROCO case, I will have my nameless input and my nameless WPS file. So for any case, these are the most important files. For you want to reproduce what someone has done, ask them for these files. Can you give me your nameless input? Can you give me the nameless WPS files? And these are text files. You can modify them with a text editor by hand. Okay, so these were this quick 1 hour presentation of words, I think you need at least 1 week or 2 weeks of lessons for a basic Word class. Maybe we can do a summer school on Word one day. But again, 2 weeks plus 6 months of experience. Is trial and error, is practice the key. But it's not too different from CROCO. So if you have experience with CROCO, you need to find the equivalents in each one. Say, oh, how do I do this? I do this in CROCO. How do I do this in Word? And you need to do. Overall, it's a bit more friendly than CROCO, so it's easier, but it's also computationally expensive. So anyways, this is what I wanted to say. Any questions?
Oh, yeah. Is there a link that download this live version, like CROCO, like?
Okay, I will put it on the server.
Thanks.
No problem. So, well, we're in the atmosphere-ocean coupling, so you need to learn Word. That's the. You want to do atmosphere-ocean coupling, you better learn how to do atmosphere modeling also. But it's not too hard. It just takes time.
One question here.
Yes?
About microphysics. Which processes are involved in the parametrization, the microphysics? Which process you want to reproduce with this parametrization?
Microphysics, I think it's more related to how you represent the water cycle in the atmosphere, like how many components you have for, if you have ice, you have graupel, you have snow, and all those aspects. Is the microphysics of the water in the atmosphere. I mean, okay. In the ocean model, you worry about temperature and salinity. In atmosphere, you don't worry about salinity, you worry about temperature, but you worry about the humidity of the humidity profile. So the water in the atmosphere.
Okay, I think I understand. Thank you.
Okay.
Andres?
Yes, Christian?
If you don't have a previous work in an area that you want to release a model, what is the step to do to release the first modeling?
For the physics?
Yeah.
I think, I don't know if you can find an area that has not been modeled already with Word. I think you will find work. You have a lot of work in the ice fields. You have worked in arid zones. So you have you can look for an equivalent configuration, an upwelling area, or like a land sea boundary. I think it will be hard to find an area that has not been modeled. There are many experiments of global regional simulations, and you can, but if not, you just trial and error. I mean, just try, compare with data, and see if it's working or not.
Yep. Thank you.
Okay, so I will stop now. We can have a short break, 10 minutes, and then we will have we'll go into the details of the coupling tools by Leonardo Renaud.